Hello, welcome to lecture 2. In this lecture, we will introduce a problem called polynomial identity checking. And then we will talk about a randomized algorithm to solve this problem and analyze its performance. After that, we will introduce two basic concepts in probability. The first one is conditional probability, and the second one is independent event. And after that, we will see how to improve our methods, our randomized algorithm for checking polynomial identities using this conditional probability idea. In particular, we will introduce the sampling with replacement and the sampling without replacement ideas. Okay, so let's start. So let me define the problem for checking polynomial identities. The input has two parts. The first one is a function f of x, and this function is in product form. I will give you an example of what a product form looks like. And the second part is another function, g of x, and then g of x is in canonical form. So that means that somehow we have two functions, f and g. And our question here is whether f and g represent the same thing, whether they are the same function. So what is product form? What is canonical form? So this is an example. So the product form is to write the polynomial in terms of the product of these monomials. So f of x here is the product of the three terms, x minus 1, x plus 2, and x minus 3. And then g of x is the traditional form. So this is called the canonical form when we try to expand the formula, the function, so that we get no product here. So we have now two input functions, and then we want to check whether these two are the same. So at the first glance, maybe it seems that they are the same, but actually in this example, they are not. There was actually a mistake here when computing the coefficient of this x term. It should actually be minus 5. But here, we do not know without really checking, okay, or really verifying whether they are correct or not. So we want to find out whether there are clever methods to do so. So the first method is the brute force method. So what we do here is, originally, fx is in the product form. So what we can do here is, we try to expand f of x and make it into the canonical form. So once we have the canonical form, then we can compare the results with g of x and see whether each coefficient matches. So how fast is this method? So we say, okay, so let's say d is the degree of f of x. So the number of monomial terms in fx, or the highest term in gx, whatever. Okay, so let's say d is the degree. And the brute force way to expand f of x, you can do so in d squared time. So for instance, so let's get back to this one. So to expand this, we may first compute x minus 1 with x plus 2 multiplying together. So we need to multiply x with x, and then minus 1 with x, and then x with 2, and then also minus 1 with 2. Okay, so there are like 4 operations. Now after that, we will have a degree 2 polynomial, and then this degree 2 polynomial is multiplied with this x minus 3. So each term, there are 3 terms here, will individually or separately multiply with x and minus 3 respectively. So there are now 6 more computations, and then 8 more, and then 10 more, and so on and so forth. So in the end, if there are d terms here, which means that the degree is d, then in that case, we are going to use order d squared total computation time. But then actually, we can do it a little bit faster. There is a method called Fast Fourier Transform, which can do the whole process in order d log d time. But even so, we still want to see whether we can do it faster. So let's see. We have now the second method. Now this second method is a randomized method, and it is actually a very lazy method. What we are going to do here is, we are going to choose a random number c, okay? And then we want to compute, okay, the value of f of c and the value of g of c. So we are not expanding everything, but we just are interested in the value of f of c. We are interested in the value of g of c. And then we compare whether the value f of c is the same as the value of g of c. If they're the same, then we will report yes. So we will just use this single match, whether they are the same, to determine whether the two polynomials are identical. Okay, if they are not, obviously, then we find some reason why they do not match. Okay, so they are different. So in that case, we report no. And how fast is this method? Okay. So here, we again let d to be the degree of f of x. So computing f of c takes order d time. So why? This is very easy. So if you look back to this one, so what we do here is that if we want to compute f of c, then we will have the c value here known. Okay, so we know that what is the value of this one? C, let's say c is equal to 5, then I can compute 5 minus 1, so I get a 4 here. And then I can compute 5 plus 2, I get a 7 here. And then I compute 5 minus 3, I get a 2 here. So each term can be computed in constant time, and then I multiply it together. So in total, there are d terms multiplying together, and then so it takes order d time. Okay, the problem here is actually, if I give you a value of c, how to quickly compute, let's say this is 5, how to compute quickly 5 to the power 3 minus 2 times 5 to the power 2 minus 4 times 5 and then plus 6. Now notice that 5 to the power 3, if we do a brute force method, so 5, 5, 5 multiplying together, it takes time. So we want to do something that is smarter. So here, computing g of x actually can also be done in order d time. So how do we do so? So the idea here is we first change the g of x into a form that can be that facilitates computation, make it easier to compute. So this is our example, x to the power 3 minus 2x squared minus 4x plus 6 in our example. So what we do here is we transform this one into the same form. Look at it. So first of all, instead of getting x to the power 3 minus 2x squared immediately, we get x minus 2 only. And the x minus 2 will then be multiplied by x, so that it becomes x squared minus 2x, right? And then minus 4, you take one more term. All together, multiply with x, and then in the end, you add 6. You will see that this form is exactly the same as this one. They are representing the same function. But this term, if we have the value of x known, so for instance, let's say we are choosing c equals to 5 to put in this formula, then I can have 5 minus 2 computed easily, right? 5 minus 2 is 3, and then 3 multiplied with 5, and then we get the result minus 4, and then we get the result multiplied by 5, we get the result plus 6. So in the end, each of this bracket or each of these term can be done in constant time. So they are all together d operations. So altogether, order d time to compute g of c. So computing fc takes d time, computing gc takes d time, so overall time is order d. So it is faster than our method 1. Okay, now, is the method always correct? Okay, so let's go back a little bit. So here we are assuming that we are choosing a random number c. So let's be more specific. Here, what is meant by random? So let's say the random c comes from the collection of 1, 2, 3, the integers 1, 2, 3 up to n. Okay, so we are picking a random integer from 1 to n at the beginning. So let's analyze the performance of this algorithm, assuming this one. Okay, so is this method always correct? Obviously, no. Okay, if it is the case, then people will always use this. There is no fast Fourier transform. So first of all, in order for this method to be wrong, then the original f and the original g should be different at the beginning, because otherwise, if they are the same, then we will never make any mistake. So first of all, it will be wrong when f of x is not the same as g of x from the start. And also, for the random number c that we selected, we find that f of c is the same of g of c. So they are different, but then the random number c fools us. It makes us believe that they are the same, but they actually are not. So for instance, so let's see a new function fx. So here fx is x minus 1 times x plus 2. And then we have gx is equal to x squared. So if you take a look quickly, then these two functions, they are not the same. But on the other hand, suppose that we are very unlucky. We are selecting the random number c to be equal to 2. Then what will happen? The left-hand side, f of x will be 2 minus 1, which is 1, multiplied by 2 plus 2, which is 4. So you get a 4 here. On the other hand, g of x, after computation, you will also get 2 squared, which is equal to 4. So which means that if we apply the random algorithm, the randomized algorithm, for this input f and for this input g, then there is a chance, at least the chance that when we are selecting the random number c to be equal to 2, then we are making a mistake. So how likely is this mistake? This is actually what we want to ask next. So is this method always correct? No. But how likely is a mistake? Okay, so let's see. So in order to get a mistake, actually, we need to get a bad random c. Yeah. It is the random number that will fool us into believing that two functions are the same. But for this c to be bad, we have f of c is equal to g of c, which means that it has to be a root of the function fx minus gx is equal to 0. So it has to be a root of this polynomial. And then we claim that there are at most d such bad numbers exist in the whole universe, in the whole world. The reason is that this is a polynomial with the highest degree d, and similarly g is a polynomial with the highest degree d. If they don't match in their degree, then we can tell they are different immediately. So assuming that both of them agrees in the highest degree. So in that case, fx minus gx will be a polynomial in highest degree d. And by the fundamental theorem of algebra, we know that such a polynomial has at most d roots. Okay, these roots could be real, could be complex, could be integral, whatever, but there are at most d of them. Because of this, and then since we are selecting a random number from n possible numbers, so the chance of getting error must be at most d over n. In practice, it could be much fewer than, or the probability will be much the error probability could be much smaller, because if the function does not have, or if this polynomial does not have any integral roots, maybe there is no here that will make a mistake. Okay, but in the worst case, at most d numbers in the universe will make it bad, and then we are selecting a random number from n possible choice, so the error probability is at most d over n. Okay, so we now have a randomized algorithm that runs in order d time, and then the error probability is d over n. So if n is large, then in such a case, then the chance of getting an error will be small. Okay, so this is the first part of this lecture. So let us now continue with the new concept. Okay, so we will talk about conditional probability and independent events. So first of all, conditional probability. Let E and F be two events, and then we assume that F is an event that must occur, so we have probability of F is greater than 0. So we define something called conditional probability. The probability of E, given the knowledge that F must occur, will be denoted by this term, probability of E with a vertical bar F. So it reads as probability of E given F. So given the knowledge of F that it has to occur, then what is going to be the chance of E to happen under this scenario? So what does that mean? So if we look at the Venn diagram, so this is a general case of a Venn diagram for events E and F. Okay, originally probability of E is the total probability of the outcomes here. Okay, but now it is not the case. It is the case that we are telling you that F must occur. So we only focus on all the outcomes within this region of F. And then, knowing that F must occur, if we now want to find what is the chance that E occurs, then we are looking at these particular outcomes. Okay, so what we are going to do here is that we are actually finding what is the probability of the outcomes here compared with the probability of all the outcomes within this region. So that's why probability of E given F is equal to the probability of this part E intersect F divided by the probability of F. Is that okay? So given F, we restrict our attention to only those outcomes within this F. And then we want to find the ratio between the outcomes within the intersection E and F with the outcomes in the whole F. Okay, so let's have some example to check our understanding. Okay, so here, the first example here is we have a bag with 3 balls. 2 of them are red and 1 of them is green. And what we are going to do here is we are going to select 2 balls randomly, one after the other. So we pick 1 ball out, and then with the remaining 2 balls, we pick another out. Okay. Let us define E to be the event that the first one is a green ball. And F is the event that the second ball is red. And then we want to find out what is the probability of E given F. Okay, so let's go by the definition. Okay, so what we are going to do here is we want to compute the probability of E intersect F and the probability of F. We want to find out what is the ratio between them. So this will be our desired result. Okay, so first of all, let's take a look at the sample space here. So we are picking two balls from three balls altogether. 2 of them are red. So to help our analysis, let us label the red balls as R1 and R2 and label the green ball as G. So when we are selecting 2 balls, so the possible outcomes are as follows. We may select R1 and then R2, and then the next one is we may first select R2 and then R1, or we may select R1 and then the G, or G R1, or R1 this one R2G, or GR2. So altogether we can see that there are 6 possible outcomes for this experiment, and then each of these outcomes are equally likely. So let us find out what is the probability of F. The probability of F concerns with the second ball. So what is the chance that the second ball is red? So the second ball is red. Let us take a look of what are the outcomes that correspond to this F. So this outcome has the second ball red. This outcome has the second ball red. This outcome has the second ball red. And also this outcome has the second ball red. So there are altogether 4 outcomes out of these 6 to have the second ball red, and they are all equally likely. So because of this, probability of F is equal to 4/6. And how about this one? What is the probability of E intersect F? So E intersect F means that I need E to happen and I also need F to happen. So the first ball has to be green and the second ball has to be red. So we will see that this is one of the cases that matches E intersect F, and this is another one. So there are actually exactly 2 cases out of 6 cases that E intersect F will happen. So the probability of E intersect F will be equal to 2/6. And because of this, the ratio will be 1/2. So probability of E given F is equal to 1/2. Now this is the first way to think about this problem. But there is actually a much simpler way if we understand what is meant by given. Okay, the idea of given a certain event happens. So let's take a look of another interpretation of the same problem. So remember, okay, here let's recall a little bit. Okay, what do we know? We know that the second ball is red. And what do we want to find? We want to find under this condition, under this knowledge, what is the chance that the first ball is green? Okay, so we know the second ball is red. We want to find out what is the chance that the first ball is green. Okay, so this is what we should remember now. Now, knowing that the second ball is red, then what does that mean? So the second ball has already been a certain red ball, so we take it there. Then in that case, the first ball has to be chosen from the remaining two balls, and then we know that one of them will be red and one of them will be green. And then these two balls will be selected as the first ball with equal probability, right? Because we are picking balls randomly, so we do not favor any particular ball. So because of this, there are two balls to be selected. The chance of selecting a green ball, which is what we want, is 1 out of 2. So probability of E given F is 1 over 2. Okay, simple, right? So if you are okay with this, then let's go to a more complicated problem. So here, suppose that we have 26 red cards and 26 green cards. We are picking 3 cards randomly, one after the other. Okay, we now have two events E and F defined as follows. E is the event that the third card is green. And then F is the event that the first two are red. So what is the probability that E will happen given that F must occur already? So if you understand the whole idea, then what does that mean? F tells us that the first two are red. So by the time that we are selecting the third card, okay, there are just 50 cards that we can take. And then 24 of them are red, 26 of them are green. So altogether, 26 green card will be what we want, and then it is going to be selected out of 50 remaining cards. So the probability of E given F will be equal to 26 over 50. Okay. Yeah, make sure you understand what is going on. And actually, if you don't believe, that's okay. That's really okay. So what you can do here is that you can draw out the sample space and then do the counting and confirm whether this is correct. Okay, so this is conditional probability. And then independent events. So what does that mean? Okay, again, this time we have two events E and F to begin with. We say E and F, they are independent. So this is a definition. If the probability of E intersect F is equal to the probability of E multiplied by the probability of F. But you may ask, why? Why do we call them independent? So it doesn't look like, yeah, from the formula, there is nothing like independent at all. So the reason actually, if you now know what is meant by conditional probability, then we can have a theorem now. Okay. So events E and F, they are independent if probability of E given F is equal to the probability of E. So why? So we can easily prove it. Because probability of E given F, this is the conditional probability, this is equal to the probability of E intersect F divided by probability of F. So if we replace this one as E intersect F divided by F, then in that case, after doing rearrangement, we will have probability of E intersect F is equal to probability of E multiplied by probability of F. We get the formula in the previous case. Is that okay? So if this happens, then the previous page happens. So in that case, if this happens, then the events E and the event F are independent. Now, if we look at this formula, it makes more sense to talk about independent. So what does that mean? Here, it means that originally I have some idea about how frequent that the event E will occur. So let's say the chance of having a beautiful day today is 0.7, something like this. And now we have an event F. So let's say someone tells you that, oh, Kai is pizza this morning. Okay. So you know I have eaten pizza already. Okay. If you know this fact, and it turns out that it doesn't affect your view about how likely that the original event E occurs, so the chance that we have a beautiful day today, given that you know that I eat pizza, if it turns out to be the same as I don't know this information at all, then in that case, the two events seems to be unlinked. They don't have any connection at all. So in that case, we say they are independent. So if we look at this as our interpretation of independent events, then it makes more sense. Telling you what happens for a certain event does not affect your view of the probability. Does not affect means that it does not increase or it does not decrease. It doesn't change at all. Okay, so in this case, then the two events are independent. Okay. So let's see some example. So the first one is, suppose that in our experiment we are doing two things. First of all, we are rolling a fair die, and then we will flip a fair coin. So the experiment will contain the result of the fair die and the result of the fair coin. Let E to be the event that the result of the die is 2, and let F to be the event that the result of the coin is a tail. Then obviously, E and F are independent. If I tell you what happens about one thing, so if I tell you, oh, the result of the coin is tail, does it affect your view about what is the chance that the result of die is 2? It doesn't, right? Because one is about the die and the other is about the coin. So they are all together, they are very different things. So one do not affect the other. So in that case, they are independent. So if it appears to be independent, then it really should be independent. But we have another example. So sometimes we need to be careful, okay? So this time we are going to roll a fair die 2 times. We let E to be the sum of the results of the 2 rolls, is an even number. And we let F to be the result of the first roll is even. So we want to check whether these two events, they are independent. So we are going to use our new theorem. We want to find out what is the probability of E and what is the probability of E given the knowledge that F occurs. Okay, so let's do the analysis of these two probabilities. So E is, so this is just a recall, E is the sum of the results of the 2 rows is even, F is the result of the first row is even. So the chance that E occurs, so if we look at all the possible outcomes in the sample space, so there are altogether 36 outcomes from 1, 1, 1, 2, 1, 3 up to 6, 6. Okay. So by checking all these 36 outcomes, we can easily find that 18 of them will have the sum to be an even number. And since they are all occurring equally likely, so the chance of E happening is equal to 18 over 36. Now, how about the other case? The chance that E occurs given that F occurs. So I tell you that the result of the first row is already an even number. So in order to have the total sum to be even, that means that the second row will be even. So what is the chance that the second row has an even number? Then this is equal to what? This is equal to 3 over 6 because there are 3 cases. There are 3 even numbers on the die, right? Out of 6 numbers. Now 18 over 36 is 1 over 2. 3 over 6 is also 1 over 2. And then we see that these two terms are the same. So in that case, E and F, they are independent. So here, this example says that sometimes when events doesn't appear to be independent, they may still be independent. So we need to check carefully. Now, independent events, they are something that is very good for us. So in particular for the analysis. It will make the analysis easier. So when we discover certain events to be independent, then we will try to make the best use of it. Okay, now let's get back to the case of, can we improve our method 2? So can we improve our randomized algorithm for checking polynomial identities? So in particular, we want to decrease the chance of making an error. Now this is the current bound. The current bound says that the chance of having error is less than or equal to d over n. So the first idea here is simple. Yeah, because the error bound depends on d and n. D does not change, but n you can change. So if we apply a larger n, so when we select a random number from a larger universe, then in such a case, you can drop the error probability immediately. So this is a very easy way to do so. But then sometimes we may not do so. Yeah, it seems like, yeah, just by changing the n, we don't need to pay anything, and then we can immediately improve the algorithm. So it doesn't make sense at all. So there's no free lunch, right? So we do nothing at all, right? But then we are suddenly doing things much better. Now, actually, this is not free. The reason here is we need to, so selecting a random bit is easy. We just need to flip a coin. But selecting a random number from 1 to 1 million, you may need to flip a random coin many times. So this is the resource, we call it the random bits, that we are making use of. So by increasing the n, we are actually requiring a more sophisticated random number generator, or we are requiring more number of random bits to do so. So this is some resource that is paying for the improvement of the algorithm. So idea 1 is good, but then it may not be used because we may need a lot of random bits. But then there is a second idea I guess most of us are aware of. So we can try to rerun the algorithm. So we run it again and again. Let's say we run it for k times. Maybe we are unlucky in the first run. Maybe we are unlucky in the second run. But as long as we are lucky in some of the runs, then that's good. We will discover that the two input function f and g, they are really different. Okay, so suppose that we use this method, rerunning k times. We let ej to be getting a bad random number, which will fool us at round j. Now, in order to make a mistake in the end, we have to be very unlucky. We have to get a bad number in the first round, and we have to get a bad number in the second round, and so on and so forth up to the kth round. So we need this to happen, E1 intersect E2 up to EK. So this is the case that we are having a bad number in each round. Okay, so let's see how this term can be simplified. So this term, by using conditional probability, so this will be equal to the probability of EK given E1, E2, E3 intersect together, multiplied by probability of E1, E2, E3 up to EK minus 1. Is that okay? So these two multiplied together should get this term. And now, if you look at this term has the same format as this one. Somehow like this, intercept of all the events. So we can do the same process to make it into the probability of EK minus 1 given the intersection of all the remaining first K minus 2 events. We can continue this process to do so and so on and so forth again, so that in the end, we will get a formula like this. So in the end, we will get, so we are this one, we get this term, and then expand this one, and then we get this term, and then expand this one, and so on and so forth. So in the end, each one of them will be like E of one event given some other events intersecting each other. So this is what we have. So after doing the rewriting or using the conditional probability formula, we get this is probability of E1, multiplied by probability of E2 given E1, multiplied by the probability of E3 given E1 and E2, and so on and so forth. So this is how we can make this happen. Okay, so let's see how we can find out, okay, all these probabilities. Okay, so let me copy the formula here. Okay, now when we are doing the rerunning of the algorithm, so when we rerun it, each time we need to pick a random number. So suppose that we restrict that we cannot pick the same random number again and again for each run. So we pick a number, we memorize it, so that next time we will never pick it. So in that case, the probability of error can be written as like this. So first of all, it is equal to this one, but the first term is less than or equal to d over n. So we have proven this already, right? The chance of getting a bad number is less than or equal to d over n. And how about the next one? The next one says that I already know that bad events happens. That means that I have already used up one of the bad number. So the chance for the next case, the next round to get a bad number will be there are only d minus 1 bad numbers left in the whole world. And then we are selecting a number from n minus 1 remaining numbers. So the chance for this probability will be, again, using the similar idea, is less than or equal to this number. So we can have probability of error less than or equal to this one. So we have d minus 1 over n minus 1 here. And the next term is d minus 2 over n minus 2 here, and for that one, and so on and so forth. So there are k terms. So this is the case that we are not allowed to choose the same number again and again. But of course, we can be lazy. We can just rerun the algorithm without memorizing anything at all from what we have done in the past. So in the case of this one, then the chance of having error in the first round is d over n. And the second one is whether because I'm rerunning the algorithm without caring about what has happened previously, so actually these experiments are independent of each other. So the event that the second round to be getting a bad number will happen, even though I tell you that the first one has a bad number, will not be affected. This chance will not be affected. So it is again d over n. So when we allow the same random number to be chosen, then the probability of error can be analyzed like this. So if this is the case, then good. So what does that mean? So we have two ways of doing the improvement. One is, okay, both of them are rerunning the algorithm, but one of them allows the same number to be picked again and again, and the other one does not. So which one is better? Okay, so for this one, you will see that this term drops, and in the end, if we have k greater than or equal to d, actually it becomes 0. But in such a case, then the total running time, actually we are running d rounds, and then each time we run all the d times, so it doesn't look good because the total time is already d squared. But in that case, we will see that each term here that we try to multiply will decrease. But for this one, it will not decrease. So this one will have a better or a smaller probability of getting an error. But on the other hand, this one is better for the analysis because all the things here are independent, and what? And this one allows us to be lazy. We don't care. We just rerun it. Okay. So in the end, let me introduce the two terms, okay, that we want to tell you before. Okay, so first of all, we are doing a process of picking a random item. And this process is usually called sampling. We take a sample, okay. And if we allow the same item to be chosen, so it is like the scenario that we pick an item, put it back before we pick the next one. So in this case, we are putting things back. So this method is called sampling with replacement. So otherwise, we don't put back. So in this case, the method will be called sampling without replacement. So usually, sampling with replacement is easier to analyze and easier to implement. Okay, thank you. So that's all for this lecture. Thank you.